Hey class, I wanted to spend today's lecture talking about algorithmic runtime complexity, and we only have a few weeks left in this semester, maybe 2 more full weeks and then study week or exam week. I suppose I could check the syllabus, but we're just going to roll without knowing. So it's on there, the date of the final exam. I believe it is Tuesday, May 4th. So, Star Wars Day for those of you that observe it. So, really, we've already covered all of the topics in the semester, or at least we've gone over them that we need to for the subject. But it's nice to reinforce it. So, today I wanted to talk about algorithmic complexity. And the easiest case to study that is with sorting. So we'll write up bubble sort. We'll evaluate how bad it can get, and then we'll see if we can find a general way to ask it so that we can gain expectations on what the best we can do in terms of guaranteeing a solution in a given runtime. And as we'll see, it varies based on the problem that you're asking your algorithm to address. So let's begin with bubble sort, and we'll go on from there. Okay, so we can try again. There's got to be a way to zoom. Sorry. Okay. It's uncomfortably large on my end, but I do think that is easier to read. Okay, so let's make sure everything still runs. Excellent. Okay. So the first thing we need is an array. So we'll create a numbers array. We need to make sure it's not sorted. So we'll start with 0 and then we'll just spiral our way out. And 6. Okay, I think that's good enough. Okay, for loop. Iterate over the collection, so it has the standard form. You declare an iterator, you give it its, you bound it above, and then it's again 0 indexed, so that it runs from 0 to n-1. So if it reaches the value equal to the length, then it terminates. And then you increment, right? Standard stuff. Okay, so let's print out our numbers, run it. Excellent. Okay, well, we're going to talk about runtimes within a function, so let's go ahead and wrap this within a function. We'll call it sort because we know we're going to want it to sort. Rename the array. And then we'll move this declaration to below. We have to change the references. And then let's go ahead and correct this because we know that we're going to want to track a sorted collection. But we should be able, or we will be able to update the array contents, the values of the array itself, so that when we return the sorted array, it's a reference to the input array. However, if you don't like that, then you can create a new array. So const sorted array, which is equal to the original one, except you have a slice. And when you don't pass in any parameters, it copies all of the contents into a new one. And so we'll return sorted, and then all of our tests will be against sorted. That way, we now have a function which guarantees that the input value is not molested, and we return that value, or we return a new sorted collection. We'll pass in the numbers. Okay, so we're still not actually doing anything but printing it out, and then returning the unmodified value. That still works. Okay, we haven't actually broken the nothing that we've done so far. Okay, so now bubble sort, we can do it with just a single loop. The trick is going to be, whenever we make our comparisons. So with bubble sort, we start at the beginning and we compare one item to its neighbor, and then we progress all the way through. So because we're going to look forward, because each iteration through the loop actually has a span of 2 elements in the array, we have to make sure that that second element is properly bounded. So now we take one less iteration through the loop because we're dealing with these adjacent items within the array. Okay, so now we say, so we're sorting ascending, and we can rename this sort ascending. And we say, okay, so if the current item is greater than the succeeding item, then we want to swap them. And so we'll create a temporary variable, we'll call it swap. So that equals the current item. And then we overwrite that current item with its neighbor. And then we assign the value that was formerly in this slot to that neighbor. And so hopefully you've all seen bubble sort before. And then we repeat this. So we reassign it to -1, so that when it iterates, it continues at 0. And so it's like passing through the first time. So anytime there's a swap, we reset the iterator. Oh, okay. Well, it ran, but we're not printing out the numbers. So let's call print collection or print array. And again, we can just loop through it for now, but we could put it on a single line if we were so inclined. We might do that later. Okay, so our replacement isn't working. So let's run through each time. We'll see if we can print out just the array. Oh, of course. So we're making all of our modifications to sorted or to array, and they really should be compared to sorted. Okay, there we go. So that's it. There's another way we can formulate this. So rather than doing this trick, we could create a second loop. Where we have a second iterator, and it begins at this location, and then it runs to this location. Wait, sorry, I have that backwards. There you go. So this one stops at n minus 2, and this one stops at the second to last item, and this one stops at the last item. Okay, and then we perform this part. But we don't reset this. So whenever we perform a swap, we break, and then we do it again. So I believe that would work. Let's check it out. No, that's not quite right. Well, now that we've talked about it, we kind of have to solve it. Okay, so we're using I and I plus 1, but really this should be J. I plus 1 should be replaced with J everywhere. Still not quite right. Okay. Oh, well, okay. Yeah, I guess we almost have to include that. So then this has no obvious benefit to doing it that way. So we'll just discuss it in this format, right? Where I think it's a little bit easier to read. So you can clearly always reach a point where you're resetting, but how many times can you do that? What's the most number of times that you're going to have to deal with that reset? So let's we have an array of 7 elements. Let's work through it just a little bit to see what's happening according to our algorithm, and then that should give us a hint what we're looking at, and in particular how to count it and develop a function that represents the runtime of what we're doing, the number of loop iterations. Okay, so there's our array, spanning from -5 to +6. And so we have our loop, the sort ascending function. And so we begin by comparing this one and this one. And if this is greater than this, we perform a swap. So we do that. So we have I equals 0, and then the action's done at this point when I equals 0. It modifies it to this array. So 0 is greater than -1, so we perform a swap so that the item on the left is less than the item on the right. Okay. And then we also perform the action of resetting the iterator. So we're setting it to -1 because when you reach the end of a loop, or when you continue from within a loop, it runs the incrementer portion as a suffix, as a trailer, an appendix, or whatever. It's this operation that follows whatever is in the body of the loop. So we set it to -1, and then it runs the incrementer. And then the next time it enters the body of the loop, it's again 0. So we actually want it to be 0, but we're accounting for the incrementer, so we're setting it one behind where we want it to be when we return. So again, we start with 0, and then we run our test. And that first item is less than the second item. So whenever there's no swap, there's no state change, we'll just put a check mark so that we know that it's the same as before. And then for I equals 1, we compared 0 and 2. 0 is less than 2, so we're fine. And then we compared 2 and 3, or with values of 2 and -3. And so -3 precedes this, so we perform a swap. And then we tell it to go back to the beginning of the loop in order to reset the iterator. And then we'll again go through, check, and then, check, and then we'll see that -3 is less than 0. So then we'll do another swap, and so on and so forth. So you can see that there's a lot of restarting. I mean, if you were having to do something like this by hand, then it would be extremely annoying. So imagine you were given this unordered collection of pictures, like just pictures in a warehouse, or picture frames, and inside each frame, we'll use a number, was a number. You were told, okay, I want you to hang each one of these pictures in this house, by ascending order. So start with the first one and then so forth. And if you started hanging, and each time you found one that was out of order, you went and you moved all of the pictures one by one over until you found the proper place for the whatever number you're currently on. And then you started again. You went and you got the next picture and you hung it up, and then you had to take them down and go through and slide everything over again. It's just kind of an absurd amount of a work. It's extremely inefficient. How inefficient is it, right? The easiest, or we can tell that this algorithm is going to be at its worst whenever the items are sorted in reverse order. So whatever the if you're sorting ascending, then if you get a list in descending order, then it's going to be at its worst. And if you're sorting descending, then getting a list in ascending order is going to be at its worst. Right? So in the case that we were doing, where we're counting from least to greatest, then getting something that's sorted from greatest to least is going to cause the most amount of problem. And in such a case, right, we would have the greatest element over here. So we would have 6, 4, 2, 0, -1, -3, -5. So we compare the first two, and it's out of order, and so we perform a swap, and then we start over, and then we get a check on that. Then we compare the second two, and it's out of order, so we perform a swap, and then we start over, and because we had swapped those two, we now have to make that swap again. So we make we're making a little bit of progress each time, but whenever we reach our new furthest point, we have to start all the way over again and do in plus 1 operations to get the next furthest point and have some sorted beginning of the list. Right? So at first there's one correction, and then to get the first item, to get one sorted item, and then there's two corrections to get two sorted items, to get 2 places sorted, and then there's 3 corrections to get 3 places sorted. So it's 1 plus 2 plus 3, and we've seen this. It's this, right? The sum of n items or whatever. Right? Whenever you have to add up the first n integers, then this is your function. So it's n squared. It's on the order of n squared. And then so that's your runtime. Okay. So that's the worst case. So now the question is, can we do better? Well, we should know that we can do better because we've discussed merge sort in this class, and merge sort has a runtime of n log n. So the number of operations that it takes to combine it at each stage, you're looping through in items, each time, and then the number of times that you have to perform those loops, or the sum of those loops, is at each stage when you're combining the leaves. When you've broken it down into a bunch of leaves, and then you're going back up so that you have these parent arrays that contain 2 items and then 4 items and so forth, and so it's like going back up a tree, and so at each level you're doing n operations, and then there are log of n levels because we're dealing with tree height, or log base 2 of n levels because we're dealing with a binary tree. So we know that one has n log n operations, and that's better than n squared because the logarithm grows more slowly than linear, right? So it's slower than linear and also slower than constant time, and slower than logarithmic time itself. But n log n, in terms of doing something, right? In terms of actually solving a problem, it's hard to beat n log n. You can beat it in lookups if you leverage memory. If you're just willing to occupy up a lot of space in memory, then you can get faster time in lookups and writes as a result because you know exactly where you need to write to. So you can beat it there. But in terms of and then if you need to visit everything, you need to perform some action on every item in a set, then you can do that in linear time just by visiting each element and going in sequence. But in terms of modifying a collection, or performing some action that you know that organizes something, you're not going to beat in log n. That's essentially as well as you can do. It means you went through the collection once, right, and then you had to perform some amount of work in order to change it to some desirable state. And when that amount of work, when the product of iterating through the collection and that amount of work is in log n, well, log is the minimum amount of work that you would expect to do whenever you have some item that relates to the rest of the collection via some ordering property or whatever. Okay. So we know from construction that there is an algorithm that is in log n. And now the question is that the best we can do? Is there some way that we can discuss this problem, the sorting problem, so that we can know that there really isn't any better that we can do than merge sort? We can come up with other alternatives like quicksort and so forth. But in terms of like actual runtime, like it's as good as you can expect to do. So the way to discuss it is to look at this as a permutation. Okay, so we have some set of numbers. In this case, we have a set of 7 distinct integers, and they all can be, because they're distinct, they can all be compared using the less than operator. We can use this comparison operator to relate any two of these items together. Okay, so we can distinguish one from another, right? Because we can tell that one is always less than the other. So then we can discuss taking permutations on this set, because we can tell the difference between the different permutations. So if we moved -1 here and 0 over, then that's another permutation. If we were to put it in perfect ordering and perfect descending order, that's another permutation. And if we were to do it in descending order, that would be another one. So how many are there? How many different permutations are there? And we kind of touched on this when we were going through the advanced counting section. And there are, for an array of size n, in this case n is 7, so there's 7 elements. Then there are 7 factorial permutations. If we had 30 elements, then there would be 30 factorial permutations, and so forth. Okay, so in math, in algebra, we can consider, we study the set of the permutation group. We study the symmetry group. Those are the same thing, the permutation group and the symmetry group. And there are n factorial elements, and whenever it acts on a set like this, then it just permutes the order of things. It shuffles things, and so it shuffles them in the sense that it changes it. This is still algebra, so it's precise. It's not random. It's just not some stochastic model for them. But each element in the permutation group just jumbles it. It shuffles the deck, so to speak. Okay, so in particular, there's always one complementary element. So there's an inverse. Just like whenever we're discussing an addition, you could always get back to some default state by adding the additive inverse of that number. So if you add the number 10, then you would add the number -10, which is the additive inverse. And that would take you back to the identity, which is 0. In multiplication, if you had the number 10, then 1/10, multiplication by 1/10, would get you back to the multiplicative identity of 1. So now if we think of ordering in ascending order as being the identity state, right, the default state, and everything else is just some permutation of this nice and lovely ordered state that we have here, then we can imagine, well, if it's the same numbers and they're just out of order, without really even thinking it, just on without considering computer science, just our understanding of how numbers work and the fact that we should be able to put them in order, as soon as we're in like first grade or kindergarten or whatever, then there's an inverse for any one of these permutations. So if you take some set and you jumble it so that they're out of order, there's a way to, if you blindly did it, right, like if you wrote the numbers on these index cards and you flipped them over, then there's some way to shuffle them so that they're again in order whenever you flip them over. Like without looking at the numbers, you just know that it's possible to get them back in order from that current state. And so that would be the inverse action of whatever took it from here to there, right? From ordered to unordered. You can always find a way back to ordered. That's the whole claim here, right? So it's a lot of words to say that very simple thing. And so of the 7 factorial, right, they're all paired up. There's the identity one, and then there's everything and its inverse. And these pairs, these inverse pairs, fill out the rest of this. Okay. So what's the point in moving the problem over to that space to discussing it algebraically? Well, now we've counted it. We've counted the bad. We know exactly how what it is that we're looking for. So the symmetry group can be thought of as being a function. So it takes a set and it acts on it and it outputs. You can think of it as a new set, or it outputs that original set with some new property, in this case ordering. But the point is that it's acting on it, just like a function would act on an array. So then we can consider the symmetry or the permutation operation as being a function. Right? So it's a function that takes an array and outputs an array. And then, so now, while it's not so difficult to think of our computer program as a function, especially when it's just a computer program that calls a single function. So our sort function is something that takes an array and then it outputs a sorted array. So we can think of our sorting function as being this symmetry function. So, well, computer programs, whenever we've discussed them, I've mentioned a few times that we can think of them as decision trees. We have these flow control mechanisms like if and else if, switch, the for loops, the while loops, even function invocation itself, like recursively calling a function and so forth. So all of these are flow control mechanisms, and they have these decisions that are made. So if x is greater than y, perform this operation, otherwise go this other route. And so the very thing that we're counting is the number of these comparisons, right? The number of these questions that we ask the computer to evaluate for us, like x less than y, y less than z, and so forth. So how many of those questions does it take before we are able to return the sorted array. And so that, well, we're modeling this as a tree, right? So is A less than B? If yes, go left. If no, go right. Okay, so our program is a sequence of these questions, and it's with binary outputs, right? Binary. It is a binary tree. There are two possible answers to this yes or no question. There's yes or no. So our program is modeled as a binary tree, a binary decision tree. And we know that it needs to have some sequence of these questions, right, that yields a sorted array at the end. Well, it has to work for any input. So we know that it has to work for 7 factorial input, or whatever the number, right, in factorial. And then the final state, right, we can look at as being the sorted array that we're returning. So we know that whenever it ends, it's going to end up with a result that has one of these n factorial results, which is the sorted array. Or you can think of the program itself as being one of the n factorial possible execution paths that will eventually yield a sorted array. Okay. So there are n factorial final states because the program itself has to be, if we are thinking of it as isomorphic to the permutation group, then they're going to have the same number of elements. The same number of final output states, right, will match the number of elements in the permutation group. So then we need to know, well, if there's n factorial leaf nodes, then the height of the tree is going to be bounded below by the log of n factorial. So then what is the log of n factorial? Okay, so I think we looked at this earlier in the year, possibly in a homework problem, possibly just in lecture. So log base 2 of n factorial is equal to log base 2 of n times n minus 1 times n minus 2, and so on and so forth, all the way down to 1. And so the rule of logs is that multiplication inside the log is the same as addition outside of the log. And then we have a bunch of terms here. Which are all greater than or equal to. So half of these terms, half of all of these values, are going to be greater than or equal to this. Whatever's the first item after cutting it in the sequence in half. Okay. So you have all these smaller terms over here and all of these bigger terms over here. Well, these are all greater than 0. So if we round down, we can get a lower bound on it. and there's n over 2 of these. Right? So we can just shorten it and say that this, whatever it is at least as expensive as n over 2 times the log of n over 2 plus 1. Well, that's what we were claiming, right? So the constants kind of go away whenever you're doing this stuff, and you're really just looking at the variables. And so we have something which outgrows n times the log of n, right? N log n. So if you have an algorithm which executes in n log n times, such as merge sort, and now you have evidence that you can go no faster than n log n, well, then you know that that algorithm is as fast as it can be. And we arrived at that conclusion by counting the number of final states that must be represented in order to satisfy the constraints of the problem. In this case, you needed one final state for every possible permutation for an array of n elements. And so that tells us the number of final states, and because we're dealing with binary tree, a binary decision tree, we know we can compute the tree height based on that, the minimum tree height. So you can have an algorithm that goes no faster than this and guarantees a solution. So it is possible to go faster, but it won't be a correct algorithm, right? So if you just had the identity function, you take an array, you spit it back out, well, it runs in constant time, and if you pass it a sorted array, it's faster than merge sort, but it only works for one out of the n factorial possibilities that can be passed into it. So, okay. So now, let's see. All right, so now let's consider the problem of subnetworks. So we have okay, so we have some network here. Let's label our vertices. And we'd like to be able to ask questions of the network. So what are the types of questions that we might ask? We might ask whether or not a particular vertex is defined in the network. Like if we just look back at the graphs that we were discussing. Has vertex maybe. And then we might also want to know about an edge, so whether or not it has a particular edge. And then a more advanced question would be whether or not it contains a particular subnetwork, so or subgraph. So remember, a graph is defined as a collection of vertices and edges. So in order to ask the question of a subgraph, you would have to pass in a collection of vertices and edges, or a new graph instance which possesses its own collection of vertices and indices, and then have it compare that. So So it's still a yes/no question, but we're passing in a collection of vertices and edges. Okay, so has vertex, like now if we consider programming it, writing a program that would answer these questions. So whenever we construct the graph, the has vertex will be built in. As we've seen, we create this dictionary and then we just have a look up whether or not it contains something with that key. The has edge is also a lookup that is stored basically as soon as we read in the graph. But the has subnetwork is something that is a little trickier. So we would like it to be as close to a constant time comparison as possible. But it's such an abstract question that we have to discuss, well, how would we evaluate such a thing? So if the vertices have the same identifiers, right? Like if they are, if they're comparable to the original graph, then we can view this as a collection of has edge questions, right? So the vertices are passed in, and let's make the reasonable assumption that the graph that's passed in, or the subgraph in question that we're querying the parent graph about, or the proper graph, that it has sanity checks and it doesn't include any edges connecting to vertices that don't exist. Right? So we can really just look at the edges, and we can ask this as a sequence of has edge questions. So however many edges are here, we can ask that of the parent graph, and that would be our loop that would answer this question. Another way, so that's probably the most direct way to do it, is to write a for loop that iterates over the edges, and it asks g.hasEdge for every pair of vertices in it. And so that'll do it sequentially, right? And it'll have linear runtime based on the size of this edges collection, and it would go all the way up to n factorial, where n is the number of vertices here, because that's the total number of possible edges. So is there something where we can constrain it and ask a bit more reasonable question in terms of comparing our subnetwork? Okay, so let's go back to adjacency matrices. So we list this as a matrix, a 6x6 matrix. And then it's all zeros and ones. And this one, for the problem that we're going to consider, we're going to say that every vertex is self-referential, so that it's just implied that there is this reflexive edge. Okay, and then it's symmetric, so right, it would just be the reflection about the top half. Okay, so if you filled that in, then you would have, you can look at these as bit strings, right? It's just ones and zeros. So if you concatenated them into a word of 6 times 6, right? A word the size of the number of entries in your matrix. Right? So in this case, 36 bits. Then you could ask the subnetwork question more directly. So now your graph and your subnetwork are each representable as bit strings, as in this case a bit string of 36 bits. And so just then you can perform bitwise operations against them. So if you're not familiar with performing bitwise operations, it used to be more common. Now I think it's good for the exercise of learning how to use flags and so forth, and in terms of just counting whenever you're dealing with inclusion of elements, the item is either present or it's not. So then the number of different arrangements that you can make by including these items is 2 to the number of items under consideration. And then the binary representation is just an answer to the question of which of these items was included, right? If there's a 1 in the binary representation, that was included. And if there's a 0, then it's not. So we perform this bitwise operation, right? And so we have the value, so G bit string, right? And we perform a bitwise AND operation, so this is an ampersand. Right? And then H is the subgraph. And then we asked whether or not it's equal to so we perform this bitwise AND operation, and if the output of this is equal to the value of the bit string representation of our subgraph, if it's exactly equal to, then it has all of the same adjacencies, right? Then all of the adjacencies that we queried about are present, right? Because that's what this test is doing. So now we can do it in something like an atomic operation. This grows, obviously, like the size of the bit string grows on the order of n squared, because that's the number of bits that we're using. But that's not so much of a problem. So now we're no longer looking at a worst case runtime of n factorial for asking about a subnetwork. Now we can get the answer in something close to constant time. It can be upwards of n squared, but yeah, it's still polynomial, which is really satisfying what we're looking for. So now we can answer this question of whether or not a subnetwork is present. And in fact, an edge, a single edge, if you looked at an adjacency matrix with just a single adjacency, right, where just 2 vertices are connected and everything else is disconnected, well then this same question, right, would be the has edge question. So we could answer that as a question of subnetworks, and in fact subgraphs have a notation similar to subsets. Right? So whether or not H is a subset or a subgraph of G. And this is even similar to what we were looking at when we were doing our comparisons for our sorting algorithms. Which is the question is A less than B. Okay. So we can make our comparisons, which is nice, and we know the type of question that we want to ask. And so it would be nice to know whether or not we could put a runtime expectation on a question such as asking whether a subgraph with a particular property, such as a complete subgraph where every vertex is connected to every other vertex. We can, if we view this as a social network, then we can refer to this as a clique, right? So that every vertex relates, every vertex in this group relates to every other one. And so we can ask, what the maximum size of one is, or which the maximum subgraph is with that property, or if we had a particular set of vertices that we wanted to consider, then we could ask specifically about those vertices. But in order to answer the question, how long would it take to find the largest one of size n over 2, right? Or rather, to find the first one of size n over 2, where we're considering half of the elements of the graph at a given time, whether or not they exist in such a clique subnetwork. It's a little bit more challenging, but we can look at what we were doing with the sorting algorithm to find a way to answer that. So with the sorting algorithm, we found a way to count the number of leaf nodes. How many possible execution paths were necessary in order to represent a function analogous to, or that properly represented every element in a permutation group of size n. Okay, so we need to count the number of leaf nodes. How many possible final states are there for such a thing? So if we consider just the case where we're looking at subgraphs of size n over 2, then we can put some sorts of constraints on this. Okay, so we said that there were that we could represent set inclusions using 2 to the k elements, right? So here we have 6 elements. So there's 2 to the 6 numbers, binary numbers, that can represent every combination of these. And so on and so forth. Okay. So we're interested in subgraphs or complete subgraphs, which are half the size of this. So there's 3 bits in them, right? And they each are aware of one another. That's one of the ones that we would want to test. That's another one, and so on and so forth. And as I write these, you could imagine that this leftmost place is A. So the subgraph isn't necessarily going to have all of the same vertices, but it would have some of the same vertices. And we're putting the constraint on the graph ourselves, right? We are constructing this problem with these very specific constraints. And so the subgraph that we test is always going to have this complete graph property. So that inclusion in the graph means that it is connected to every other node that is included in the graph. or the subgraph, I should say. And it's just the labels are compatible between the subgraph and the parent graph. Okay, so some subset of these are going to satisfy this constraint where there's 3 bits going around. And so the number of these, right, is actually, we've already covered that as well. It's the number of combinations. So that's n choose k. So given 6, right, n equals 6, and we're looking for k equals n over 2, then there's 6 choose 3 of these, or more properly, six factorial over 3 factorial times 6 minus 3 factorial, right? The other representation for this. Okay, so this is the number of subnetworks that we need to be able to test, and a solution would tell us from this, right? It would give us an inclusion mapping from this possible set of which ones were included for size k equals n over 2. Well, as we've discussed, right, inclusions are binary. In fact, we just used that property, but now we're using it a second time, so that we get for a network with n elements, right, or n vertices, where we're selecting for clicks of size k, right, so complete subgraphs of size k, it is an inclusion mapping, right? So it's 2 to the number of combinations available, right? And so our algorithm, which answers this question, right, must support this many leaf nodes, right? 2 to the n choose k, and then that's the number of leaf nodes required in order to answer the question: does a subgraph, a complete subgraph of size k, exist within some parent graph? Okay, well, that's the number of execution paths, distinct execution paths that are necessary, because that's the number of combinations, right? So we can think of distinct execution paths as terminating at some leaf node. So it's in direct correspondence with the number of leaf nodes or final states. Well, if we know the number of leaf nodes and we know that we have a binary decision, right? H is a subgraph of G, right? Just as we had the binary decision A less than B when we're discussing sorting, then we know that it's still representable by a binary decision tree. So then, what is the height of a graph, or of a tree with this many leaf nodes? Well, the height of a binary tree is the log of the number of leaf nodes, right? Log base 2 of the number of leaf nodes. So then, what is the log base 2 of this? It's just whatever's in the exponent of the 2, right? So it's n choose k. So then, following the model that we developed in drawing conclusions about the optimal runtime for sorting algorithm, we know that based on the number of execution paths that must be supported, that the optimal runtime for for an answer to the complete subgraph problem is going to be given on the order of this. So what is this? Is this polynomial or is this exponential? Okay, so we're going to rely on some, we're going to branch out into one of the special functions. So because this n factorial over k factorial times n minus k factorial. It makes sense to take a look at the gamma function, which is a generalization of this. So, what is the gamma function? So sometimes we'll see it just defined as this recursive function. Right? Gamma of z is equal to z minus 1 times gamma of z minus 1. And it is that, right? That does hold. That was part of the reasoning for it. The formal declaration for it, or the evaluatable one for non-integer values, is given by the integral the integral from 0 to infinity of x to the z minus 1, right, where z was this input variable, times e to the minus x dx, where x is the variable of integration. So essentially there's this family, this is a generator for some family of integrals. So you get some value z, you plug it in, and then you evaluate this integral, and then that'll give you the answer. And it happens, and it was, this integral was constructed with the purpose of finding some generalization to this. And if you apply integration by parts, right, where you integrate this and you differentiate this and you apply integration by parts, then you'll continually get this piece that disappears when you evaluate the improper integral, and then you'll get something that is reduced by 1, right? So that's how we get this functional equation. So it's z minus 1. It's the integration by parts trick. So you keep taking the derivative of this and it decrements it. But you can see how that would only be beneficial to you if you were dealing with integer values of z. Right? But this is defined, almost everywhere. The negative integers, and I think 0 itself as well, this shoots off to infinity. But everywhere else, on the complex plane, everywhere else it behaves properly. So it's just a countable collection of values that causes trouble. Okay, so why did we make this harder on ourselves when we were dealing with something that was just integers, and now we have this complex value function? Okay, so I'm just introducing this to you, but there is a formula, the deduplication formula, which relates gamma of 2k to a product of smaller values. So this is the formula. Over here you have gamma of 2k. Over here you have gamma of k times gamma of k plus a hat. And then you have square root of pi and there's powers of 2 or whatever, some other stuff going on. Okay. Well, keep in mind that gamma, over here, gamma is just another representation for the factorial function. So if we rearrange this, then we get something that looks like 2k factorial over k factorial times something that's almost k factorial. But equally important, right? So we have this constant 1 over 2 times the square root of pi, but we have this exponential function on the left-hand side. So something that looks an awful lot like the combinatorics function behaves an awful lot like the exponential function. So can we close the gap between this and this so that we can say that something that behaves like this in effect behaves like an exponential function? And in particular, if we can, then we will have made the thrust of our argument. We will have related the problem that we're evaluating to a program whose execution, whose the span of their execution paths must support something that has a runtime on the order of 2 to the 2k. And the output is readily processed on the order of n squared. Basically, we take a function, or we take two graphs, and we answer the question, or we take a graph, and then we take a subnetwork size, and we answer the question of whether or not the graph has any complete subnetworks of that size. And the function, the hypothetical function that we would write to evaluate that would either return null if no such thing existed, or it would return the very first reference to it. And if there's only one, then the worst case scenario is exactly the same as the best case scenario, right? So you're only considering the worst case scenario. You're only considering this problem in the case that there are either 0 or 1 needles in the haystack, right? But you've still got to go through it. Okay, so then what is the relationship between this and this? And does it allow us to complete our claim that the problem cannot be solved in polynomial time, even though its response could be solved in n squared, but oddly near constant time. Right? Okay. Yeah, let's take a look at that and see if we can finish this off. Okay, so we're back here at the gamma function. This was the representation before. This is it after we've rearranged it. This is it after we've made the observation that this is an awful lot like this. And over here we used 2k, right? But now we're using n. So we used 2k and k, and now we're using n and n over 2, and then n over 2 plus 1/2. But it's the same relationship as before. It shows it. Yeah, 2z here, right? So we made that substitution. So z is equal to n over 2. Right? Okay, so then we have this representation, and I'm not sure why I repeated what appears to be the exact same line, but I did. Okay, so now what we want to do is we're going to group these things, right? So on the left-hand side, we have this. We have our exponential function times some constant. On the right-hand side, we have a factorial, we have another factorial, and then we have gamma. And each one of these depends on n. Right? So we're going to separate it, or So now we're going to break that part up even, right? So the right-hand side, the left-hand side got simplified to this. The right-hand side is being broken up into, one item in the numerator. We're going to call that alpha of n, and then 2 items in the denominator, beta of n and gamma of n, right? Appropriately, right? Little baby gamma of n. Okay, so alpha of n, right, is really just this, right? Big gamma of n, which is n minus 1 factorial. Or we could write it in its product notation, right? Multiplying all of the numbers from 1, all of the integers from 1 to n minus 1. And then beta of n was really this, right? This is just a substitution, but it's really this, gamma of n over 2, right? It translates into that. And again, we can write it in product notation. And then little gamma of n was really this. And so it's this sequence of terms, of factors, and then there's this remainder of gamma of 1/2 at the end. And that's just a constant. We know this to be equal to the square root of pi. You're welcome to prove that on your own. I think it's a great exercise. And then again, the product notation, and now we have that constant square root of pi that's carried out front. Okay, so now we're defining this this case because this is the case where you never find the needle in the haystack. You check every possible combination, you didn't find it, or you checked every possible one, and then you found it at the very end. So this is really the only one worth discussing when we're talking about worst case runtimes. Right? So this is equal to n factorial divided by q factorial times n minus q factorial. Right? So this was the number of execution paths that our program needs to support. Right? So we're looking at the other half of this. We're going to compare f of n and h of n later. Right? Okay, so this can be rewritten as this. Right? And so now we're going to see if we can rewrite or simplify this at all. So on the left-hand side we had this, on the right-hand side we had this, and then we changed it to factorials, then we changed it to product notation. And so that's all we've done. We've just basically restated everything that we've observed so far. So now we want to look at this sister function, f tilde of n. Right? And it's related to f of n, except that we've removed this 2 times the square root of pi. Right? So over here we had f of n was equal to this. Well, if we just want 2 to the n, right, then we need to multiply f of n times 2 times the square root of pi. Well, that's what we did. So we just wanted 2 to the n, because that was really what we wanted to talk about. And so now when we discuss this, it's the same thing, but we've multiplied it, every term, every equality statement by 2 times the square root of pi. So we got rid of it in the denominator, right? Square root of pi was over here. And now we have this 2 sitting out front. Okay? But again, it's still all product notations and so on and so forth. And then here in this step, so this was n minus 1 factorial, and this was n over 2 minus 1 factorial. And then here, we just cut out the first n over 2 minus 1 terms. Right? So that now the numerator, the bottom half of that factorial is gone. It's just the larger half of the factors. And then this was unchanged. So it's subtle, but the thing to notice is in the indices. Okay, and then this was again just the n choose k function, or in this case n choose q. Right? So we can make a similar simplification where we expand it, right? And we get rid of the first n over 2 terms, right? And we do that right here. So we begin with n over 2 plus 1. Okay, so now we want to show that this, which is our number of execution paths, is bounded below by something that's exponential. Right? We had that it was really closely related to that identity that we came up with for the gamma function, the deduplication formula. And so if we can make that statement, then we can say that it is not a polynomial runtime function. Okay, so we're going to try to relate them. We know that we have this function, right, f tilde of n, right, which is what we want to work with. And then it's going to be multiplied by something else in order to make this true. But we don't know what this something else is, so we're just going to leave it as a placeholder for now. And then it'll answer our question of how they relate, or how we can make this relationship true. Okay, so now we plug in what we had come up with for both f tilde of n and h of n. Right, so we just plug those in to start. We keep our placeholder g of n. And then some simplifications arise, like this cancels out almost everything here. Right, so we're left with just the n over here, and then there's an n over 2 term over here. Right? And then we check the denominator. Let's see, do we perform any cancellations there? No, because it's all shifted by 1/2 in the denominator. But after we're left with the n over here and the n over 2 over here, these cancel out. This 1/2 cancels out this 2 here, and we now have this relationship. And so each of these, right, the left-hand side and the right-hand side, both march from 1 to n over 2. So we can expand it and make term-by-term comparisons. So we still have our placeholder g of n, which will come into play here in a little bit. But for now, we're just comparing these two things, right? So just focusing on those, we're not sure how they relate. We line them up side by side, right, where the terms are generated on the right-hand side by this, and on the left-hand side by this. So k minus 1/2, right, it begins with n over 2 minus 1/2, n over 2 minus 1 minus 1/2, n over 2 minus 2 minus 1/2, and so on and so forth, all the way down to 1/2 is the smallest term. Then over here, it's just from 1 to n over 2, right? From 1 to n over 2. Same number of terms on both sides, so we can make this direct comparison. Compare this term to this term, this term to this term, and all the way on. Right? So we line them up, and we see that, well, this has a larger denominator, right? N over 2 is greater than n over 2 minus 1/2. And a larger denominator means a smaller value overall, right, when the numerator is held constant. Right? So then this is less than this. This is less than this. This is less than this. And so up and down the line, we just missed. Like everything was just too big in order to make this lower bound assertion that we wanted. Right? Okay. So we know that g of n can't be constant, because if it's 1, then this holds, and we're not able to make our lower bound assertion that our basically that p is not equal to np. So what we need to do is modify g of n to not be constant. So the easiest thing to do is to take a look and say, okay, well, we missed, right? This was less than this, and so on and so forth. But this is greater than this, or sorry, this is less than this. This is less than this. So if we could get rid of our, no, sorry, in the other direction. This is less than this, right? Is that correct? 1/2, and if we plugged in this, we would get 1 minus 1/2, so we would get 1/2. And that would be, what, 2? This is 1.5. Oh, in the numerator. So then this is 3/2. So then this is 2/3. It's greater than 1/2. And then over here we have, what, 2 is greater than 1? Yeah. But 2/3 would be less than 1, right? So if we could shift the sequence by 1, then we could make it work. So we're going to work with g of n in that spirit. We're going to multiply by 1 minus 1/2. Right? 1 minus 1/2. That's our largest number. So we're going to cancel that one out by multiplying by its inverse. and then we're going to divide by n over 2 plus 1 minus 1/2. Right, so that we're applying some new smallest number. So then we shifted everything, essentially one term. Right? So we got rid of the biggest and we replaced it with a new smallest. And this gives us a new sequence, right, when we factor in our new g of n function. Right? It gives us a new sequence which lines up like this, term by term, so that now the right-hand side is less than the left-hand side. Okay, so now we have this assertion, and we've identified some lower bound. And then now we're going to go back and we're going to restate what it means for this product, right? F tilde of n times g of n. Right? So f tilde of n was 2 to the n, g of n is this, and then if we just combine them, right, multiply everything out and simplify, we end up with 2 to the n over n plus 1. And then, so this is our lower bound for h of n. And this is, while it's exponential divided by linear, it's still not a polynomial time function. This is still considered to be an exponential, a function on the order of something exponential. So then we can just rename this. This is just a rebranding, essentially, of this to say that we have some new thing that we want to consider. Right? So it's a product of things that were known, but we're relabeling it so we can discuss it quickly. So now we say that h of n is greater than phi of n. Right? So it's bounded below by something that grows exponentially. So then p is not equal to np as a result, right? Because we're able to state that based on the number of execution paths you have to support in order to answer the click problem, in order to solve it, you need at least 2 to the n choose k operations, and something that operates on that order is not polynomial. And then the result of such a function, where it gives you the list of subnetworks that satisfy the criteria, is evaluatable in polynomial time. Specifically, if you consider just the case where you have one needle in the haystack, either 0 or 1 needles in the haystack, then you can quickly evaluate, in basically pretty close to constant time, right? Whether or not the result of that function, the identified subnetworks that satisfy the problem. Right. Okay. So we, yeah, I guess that's enough. Okay. All right. I will talk to you all on Thursday. Have a good evening.